Okay, good morning. Hope you're having a good one, even though it's a little bit dreary outside. This is second day on related rates. Some more examples to look at. I did get a request. That's one of the problems I'm going to do. Thank you for the request. So first of all, I think we were looking at problem 17 somewhere around the time the period ended. I don't know. That might be the other class, but so let's take a look at number 17, go through it, finish it up. I don't think we did it last time. So there's the problem on the right. At a sand and gravel plant, sand is falling off of a conveyor onto a conical pile, a pile shaped like a cone, at the rate of 10 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? And then they give you the formula for the volume of a cone. All right, so, well, that isn't what I wanted to do. Lock that in place. Okay, so here's what we know. We've got the volume of a cone right here in the top left. We are given the height of the thing is 15. And then let's take a look at this little sketch. In the sketch, I am depicting that we have a height of the cone. And we were told that the diameter of the base is 3 times the height. So I'm just calling the diameter 3 times h, 3 times the height. So if that's the case, what is the radius? The radius is half of the diameter, 3/2 h over 2. So that's what this r equals 3/2 h is. So now we've got all our, oh, and one more thing. What is it we're trying to find? At what rate the height is changing? So that's this dh over dt equals, we don't know. That's what we're trying to find. All right. So we will take our volume formula and start doing the implicit differentiation. But before we do, I make a substitution. V equals 1/3 pi r squared h. Well, we can't deal with both r and h, so I did is I took this substitution for r, 3/2 h, plugged it directly in for r. So then we have to square it. And after we square it, we arrive here. And we can simplify that too, because what's 1/3 times 9/4? When you take 1/3 times 9/4, 1 times 9 is 9, 3 times 4 is 12. 9/12 can be simplified to 3/4. So finally, I've got this thing in shape to do our differentiation. Okay, so now we do the implicit differentiation. So dv dt, then we do the power rule, 3 times, bring that 3 down and lower the power by 1, h squared, and then we need to use the chain rule on h dh dt. We can bring that together. What's 3/4 times 3? 9/4. And okay, so there it is. Now, all we got to do is make the substitutions that relate to the top there. So, see if we can see it up there. Yeah. So, in place of h, we plug in 15. 15 squared is 225. And 10 is the dv dt, so we plug those two things in, and then it's just a matter of simplifying, dividing both sides by 9/4 pi times 225. After doing that, I came up with 8/405 pi feet per minute. Make sure you put labels on solutions when you're working on related rates problems. So anybody have any comments or questions? Number 17. You want to work on number 12? Okay. I got a request for number 12. We'll insert that one right here. All right, number 12. Get this thing out of the way. Okay, here's number 12. Number 12. Number 12. Okay. So let me go get the problem, number 12, just so we don't have to go, otherwise I can't really, I don't have a book here, so we'll do this. So there's the problem. I guess I'll stick it on the top here. We can always. All right, so there's the problem. The included angle of two sides of a constant equal length S of an isosceles triangle is theta. So if you look down at my drawing here, I'm applying that. I've got the two equal sides S in between the angle theta. A, show that the area of the triangle is given by A equals 1/2 sine squared theta. That's where we want to end up. Okay, so I probably shouldn't have written it on top, but that's what we want, where we want to end up. So, all right, so how do we find the area of a triangle? Well, when all we know is two sides and the included angle. Welcome, Keenan. At the moment, we're working on number 12. And if I missed anybody else coming in, I don't think so. Okay. So I made this second drawing here where we have S. I've got these two equal sides S, and somewhere along the line, I need to find the area of a triangle, and the only formula that comes into my mind is 1/2 base times height. Well, if I'm going to do that, I need to have a height. So I drew in a height to one side. And of course, by definition, a height has to be perpendicular to a side. All right? So, all right. So now I've got an H here. And let's see. I know that if we take, so now we have a right triangle. If I take the sine of theta, I get the opposite over the hypotenuse, H over S. So we're looking at this guy right here now. So I figured that out from this picture. All right. So if we solve that for H, we now have, multiply both sides by S. H equals S times the sine of theta. So now, in place of H, I can plug that in right here. Down here. 1/2 B, the base is S in this figure, and now H, S times the square root of S. Well, if you put that all together, S times S is S squared, you look, hey, that's what we were supposed to show. That's that. So we've done part A. Okay. Now, part B. The angle of theta is increasing at a rate of 1/2 radian per minute. I'm just reading up here in the part B part. So that's this right here. That's telling you d theta dt is 1/2 radian per minute. Secondly, find the rates of change when theta equals pi over 6. By the way, that's supposed to be a pi. I don't know why that's not showing up. There. I just stuck it in there. So I wrote that down. And what are we supposed to do? Find the rates of change of the area. So now I've got all the given information and the thing I'm supposed to find. So what can we do to relate these things? So the equation we're going to use is, well, the one we got in part 1, 1/2 s squared times the sine of theta, which I wrote right down here. But you notice I wrote it a little differently. I took the 1/2 s squared and separated it. So I'm trying to set us up, what, for the product rule? Okay. One thing times the other. So now let's differentiate. dA dt equals the first times the derivative of the second. The derivative of the sine of theta is the cosine theta, but chain rule, d theta dt. Then what's the second one? Plus, there's actually more to this, plus the second, sine theta, times the derivative of the first. Why didn't I write that down? Okay, so plus the sine of theta times the derivative of the first. And that would be what? S ds dt. Okay, we don't have... Okay, let me just think about that a minute. The first times the derivative of the second plus the second times the derivative of the first. I'm going to have to work on that one separately. I'm not seeing why I left that out. So let's see what I wrote down here. S squared over 2. Yeah, I don't have enough given information to do this either because we don't know what ds dt is, do we? I don't think they ever gave that to us. Let me look at the problem one more time. The angle is increasing at a rate of 1/2. So that's the d theta dt. Got that. The rates of change of the area when theta equals pi over 6. Okay. I'm going to have to look into that because it doesn't look like we have enough given information. So I will get back to you on that one. But anyway, we got the first part done. I didn't do the second half. I was thinking that the derivative of this was a constant, and obviously it's not, because it had been a constant, then it would have been sine theta times 0, and I wouldn't have had to put it here. So, anybody see what I'm missing here for 12, part B? I'll come back. We'll hit on that right away tomorrow. Okay, so let me get back in my order here. Have we finished 18? Did we do 18? No. We talked about 18, I think, yesterday, but we only got like part way done. So let's pick up 18 again. So it's up on the top there. A conical tank with vertex down is 10 feet across the top and 12 feet deep. So that's this first drawing here. Let me just blow it up. Whoops. So it's 10 feet across and it's 12 feet deep. So just a quick picture of a cone, and there's water in it. That's what I tried to show with this circle. There's a depth there, and then the height is 12. Okay, so we got that drawn. Find the rate of change of the depth of water. Oh, the water is flowing in the tank at a rate of 10 feet. So that's this guy right here. dVdt equals 10 cubic feet per minute. Find the rate of change of the depth of the water. I'm calling that height. So dH dt, that's what you're supposed to find when the water is 8 feet deep. So H equals 8. The problem is, if you take the given formula, they gave it to you a little while ago for a cone, you get this volume equals 1/3 pi r squared h. I don't have r. Well, you can figure r out, and that's what I think we did last time. And that's where you take a look at this big picture. Okay, the whole distance across was 10. Therefore, the radius is 5, the depth is 12, and no matter where you are in the cone, the radius will be 5/12 of the height. That ratio will stay the same. So we know r equals 5/12 h. Well, we can do that by proportion. The ratio is always 5/12. The height is 8. Can you find x? Yeah, cross multiply. 40 equals 12x. X equals 10, r equals 10/3. So that's where I got this red guy right up here. So now we've got everything we need to go ahead and differentiate this thing. And I do that. I ran out of space, so I do that on the next page. Okay, so here we go. So there's a lot of prep here. In place of r, I plugged in 5/12 h. We just looked at that. And 5/12 h is 25 h squared over 144. And then finally I combine the 1/3 times the 25 over 44, and we arrive at this thing, 25 over 432 pi h cubed. And we haven't done any calculus yet. So now we got it as simple as possible. All right. So now let's differentiate. So on the left, dVdt equals, on the right, 3 times 25 over 432. So 75 over 432 pi, lower the power, h squared dH dt. So now it's time to substitute. And here comes all those things from the other page. dVdt was given to be 10. H was 8. And so h squared is 8 squared. H squared is 8 squared. It becomes 64. And dH dt is the unknown. So then just do a little algebra and get things by themselves. I first of all multiplied 75 times 64 pi, and I got 4,800 pi over 432. Now, basically, just multiply both sides by the reciprocal of that fraction and do some simplifying. Final result there, 9 pi over 10 was dH dt. I should have labeled that. What was the, I got to look back at the problem. So let's look back. The problem was find the rate of change of the depth of water. So that's going to be cubic feet. Find the rate of change of the depth. So that's going to be feet per minute. Feet per minute. Okay, so let me just write that in there. So, number 18, questions. All right, I'm going to Just stick that tangle back. All right, so let's go on now to number 21. So here's number 21. Make it a little bit bigger. A ladder 25 feet long is leaned against the wall of a house. See the picture, and I've got the picture right there. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. Hopefully not while you're on the ladder with a bucket of paint or something. That would be pretty, insecure. Ladder is being pulled away from the wall as you are up on it. But anyway, so the question is, how fast is the top of the ladder moving down the wall when they're pulling, the bottom of the ladder at a rate of 2 feet per second? And it won't just be 2 feet per second. It's not that simple. So when its base is 7 feet, well, we're going to do this. We're going to do the first. So we're going to take, there's 3 parts here. We're going to do this one. Okay? So how fast is the top of the ladder moving down the wall when the base is 7 feet? The base is, that means this X guy on the bottom here. All right, we already know X is 7. And I made a little sketch. The hypotenuse is the length of the ladder, 25. The height, we don't know. That's H. Or do we know? No, we don't know H. Gotta double check. Yeah. We're supposed to find how fast the height is changing. So we're supposed to find dH dt, and we know one more thing that I haven't said yet. We know that dx dt, that's the rate of this ladder being pulled away from the horizontally, is 2 feet per second. So here we go. Of course, how do you relate the variables h and x? It's in a right triangle, so we use the Pythagorean theorem. H squared plus x squared equals 25 squared. 25 squared is 625. I solved for h. I didn't have to, but I did. And then I took this, I decided to take the square root, and I wrote it so it's ready for calculus. So I could have differentiated it like it was right here. I don't know why I did that, but I did. So anyway, then we finally get to the differentiation. So dH dt, left side equals, and here we do the power rule, 1/2, 625 minus x squared to the negative 1/2. Chain rule, negative 2x for this negative x squared, and chain rule again, dx dt. Then I just wrote it. All right, what is 625 minus x squared to the negative 1/2? Well, that's a square root on the bottom. So I did that. The 1/2 and the negative 2 cancel. You have a negative and you have got that x left, and then times dx dt. Okay, let's substitute. So the one thing we don't know is dH dt. Just plug them in. And final result down here on the bottom, negative 7/12 feet per second. So in other words, the bottom of the ladder was moving at 2 feet per second. The top of the ladder is moving at what? A little bit over 1/2 foot per second. And the reason it's negative is because it's moving downward. That's the only reason. So this thing is moving downward, and that's the reason for the negative dH dt. That actually is, the way it should be. You get used to that when you deal with physical problems. All right. 25. So here's 25. I got the problem from the book right next to it here. An air traffic controller spots two planes at the same altitude converging on a point as they fly at right angles to one another. See the picture, the one on the left here, this picture over here. Not good if you're an air traffic controller. Two planes are headed for a collision. So we got all these facts. One plane is 200, this one down here is 225 miles from what? The collision point. And it's moving at 450 miles an hour. This one is 300 miles away and is going 600 miles per hour. At what rate is the distance between the planes decreasing? What's the distance between the planes? It's this hypotenuse here, this S. Okay, so now we can get to the problem. So I've got it summed up. The only thing I added to the picture was this horizontal coordinate I'm calling X, this vertical coordinate I'm calling Y. And how do we relate them? The Pythagorean theorem. S squared equals X squared plus Y squared, and then I solve for S. S equals the square root of X squared plus Y squared, which of course is X squared plus Y squared to the 1/2 power. And then we have all these given things. You're given this, you're given this, you're given this, you're given this. And this is what we want to find, the SDT. All right, off we go. So I start with the S formula, the Pythagorean theorem. Take the implicit differentiation, the SDT. Now on the right side, we use the power rule, 1/2 times X squared plus Y squared to the negative 1/2 power. Inside, we have X squared, that's 2X, chain rule, dx dt, plus 2Y, chain rule, dy dx. Notice that I have brackets around that, okay? Students sometimes forget that bracket, and boy, does that make a difference, because this whole result is together and being multiplied, not multiplied by 2x dx, and then this second one is just added. So the parentheses are a big deal. All right. I just rewrote it in square root form, took this X squared plus Y squared to the 1/2, made it that makes it 1/2, and then the square root goes on the bottom. All right, time to substitute. So you plug in all these numbers on the top, and you come up with negative 750 miles per hour. Again, negative means it's getting shorter. The distance is decreasing at a rate. So these planes are actually approaching each other at 750 miles per hour. And then the other question, you can do it on your own, but how long does the air traffic controller have? He's got 30 minutes to do something, otherwise they're going to crash. Looking up at the message board here. Any comments, questions? Okay, let's look at 27. So 27 is baseball question. So here it is. A baseball diamond is actually a square. There are right angles between all the bases. So we've got a picture on the left. Just ignore that picture on the right is for a different problem. So here's the deal. As you probably know, bases are 90 feet apart in baseball. So we've got the 90-foot length. A player is at the moment running from second to third base, and he's traveling at a speed of 25 feet per second. And at the moment, he's 20 feet from third base. So he's right about, where my arrow is right now. He's right about in there. I drew that on my picture down here. Here's here's the diamond. They got 90 feet. He's at this 20 foot mark right here. And S is the distance that he actually is from home plate at the moment. The reason that comes up is the last question, where it says, at what rate is the player's distance from home plate changing? So as he's running, S is getting smaller. What rate? So here's a summary of what we're given. Oh, and I need to put what we're trying. So anyway, X is 90. Actually, that's a constant because in this problem, he never gets between third base and home plate. So that 90 foot mark, that just stays. At the moment, Y is 20 feet. The speed he's going, dy dt, is negative 25. Why is it negative 25? Because he's decreasing he's making the length. This 20 is getting shorter at the rate of 25 feet per second. And what are we supposed to find? The SDT. So now we've got the problem completely set up. It's time to do our differentiation here. Well, first I wrote, what relates the variables? The Pythagorean theorem, because we have a right triangle. So 90 squared plus y squared equals s squared. And I put that into this format again. I wrote it so we're set to differentiate. Okay, the SDT equals 1/2 times y squared plus 90 squared to the negative 1/2 power. Chain rule, this is a constant, so we don't have to mess with that, but y squared is 2y, and chain rule again, dy dt. Substituting in the given information. By the way, 90 times 90 is 8100. The 1/2, the 2 on the bottom nicely cancels with the 2 on the 2y. And then just substitute the numbers from up above in. Y squared, y is 20, so y squared is 20 times 20, or 400. So there's our problem. You solve it, you come up with negative 5.4 feet per second. Why is it negative? Because it's getting shorter. So as he's running around, as he's getting to third base, he is getting closer to home plate every second by about 5.5 feet. So our calculus has given us some information about baseball. Anybody have any comments, questions? So I've done quite a few of them, but as you know, I only did like like on that one, we only did the first rate at 7. And then you had to do the other 2. So just get in there and hopefully, by the way, all right, I did a fair amount of the assignment this time. Does that make this any less important? No, I can guarantee you that when we get to the test on this chapter, you're going to have a related rates question. So this stuff is pretty important, and hopefully starting to get feeling a little bit, I don't know, you're starting to get a little bit more comfortable with it. That's my hope. Any closing questions or comments? My text messages aren't available at the moment. You can use the group chat. All right. Then I will see you tomorrow.